Hello everybody in YouTube, welcome to Embedded AI Lab channel in UNIST. In this presentation, we would like to introduce On-NAS, the solution for on-device neural architecture search on memory-constrained intelligent embedded systems. I am the first author and presenter, Bosam Kim, and I'm currently a master student at Ulsan National Institute of Science and Technology. I had the privilege of working on this paper with my advisor, Silge Lee. In this presentation, we'll start with the introduction, make a quick overview of our work, go through three proposals we had in this paper, see their results, and finish our presentation. Let's begin with the introductions. Whenever we deploy our model to the wild, we often face new distribution in scale of dataset shift. When training model does not help that much, we're gonna use new model. However, manually designing model every single time will be really exhausting. Therefore, you need to automate your model design by using Neural Architecture Search or NAS. Usually, typical NAS goes like this. You prepare the server, run NAS at the server, get a new model, and deploy. Now let's assume you got no connection with the network, so you don't have access to the server. Then you'll have no opportunity to run NAS. People may state there are no such place without the internet these days. However, there are such kind of places. Military deployment environment can be one example. Underground power tunnel can be one example. Models deployed at agricultural places might suffer from it, or it can be middle of nowhere where we call badlands. That's why we suggest the concept of on-device NAS. If there's no connection and you got no server, you can still run on-device NAS. To clarify, on-device NAS we are talking about is the neural architecture search that is directly operated on the target device. If you have on-device NAS, you can just run NAS directly at the target device, get a new model from it, and be ready to serve any problem right at the place where we found our model. To accomplish on-device NAS, the biggest challenge is the memory consumption. The gray bar at the graph shows the memory requirements of heavy NAS algorithms, and colored line shows the memory budget of popular embedded devices. It is obvious it's not even close. On-NAS is focusing on this matter, reducing memory to be the solution for the on-device NAS. Now let's take a quick overview of On-NAS. On-NAS is consisted of two big parts: preparation phase before the deployment, and search phase after the deployment. To sum up first, On-NAS is the combination of server-side two-fold meta-learning and device-side on-device NAS. For the first step, we'll search MetaCell, which will work as the basic building block of our on-device NAS. Second, we'll deploy our basic building block to the target device, unfold it into full-size model, and execute on-device NAS with memory-efficient methods. To sum up again, on-NAS is the combination of server-side two-fold meta-learning and device-side on-device NAS. In this paper, we propose three methodologies that enables the on-device NAS. For the presentation, we minimize the details of methodologies, so please check paper for the detailed information. Let's begin with the two-fold meta-learning running on the server. Two-fold meta-learning can be divided into two parts: meta-task learning and meta-cell learning. As a result of these two-fold meta-learning, we'll get the architecture and weight parameter of our meta-cell. Before that, what is meta-learning? As I don't have much time to explain with details, I will just focus on the essentials. Meta-learning, gradient-based meta-learning, to be precise, makes model to find optimal initial parameters. If our model have optimal initial parameters, model can adapt to certain tasks quickly with only few samples. Now return to twofold meta-learning. Meta-task learning, which is the first part of twofold meta-learning, is a typical meta-learning what other researchers did in previous works. In this part, we'll make our model easy to be adapted for the given task. As a result, we'll get the optimal initial model with their architecture and weight parameter at this meta-task learning part. The other part of twofold meta-learning is meta-cell learning, which we proposed in this work. In this part, we'll interpret our model as a sequence of adapted cells to proceed our meta-cell learning. This meta-cell learning will make our cell easy to be adapted to the full-size model. As a result, we'll get the optimal initial architecture and weight parameter of our cell. After these two parts, we'll ultimately get the meta cell, which will only take 1/n amount of storage space to save. This meta cell will contain information of tasks and models learned from the previous meta learning, and that's why we call this state folded. After the deployment, this folded cell can be unfolded by simply repeating its weight and architecture to create full-size model. After the deployment of NAS, as we reached our target device, we need to reduce the peak memory now. Before that, as we wrote in our figure, we need to unfold the cell into full model. Now we need to know how cells are consisted of. Cell is a basic building block of our parameterized model, which is utilized during the NAS. Take a look at the figure. Cell is an expression of directed acyclic graph consisted of edges and nodes. And these edges are controlled by architecture parameter beta. Now, how does this edges composed of? These edges are composed with number of neural operations, and this is the place where operations are actually computed. These operations itself will be controlled by architecture parameter alpha. Now we know our over-parameterized model has three-level structure: operations, edges, and cells. Model is consisted of cells. Cells are consisted of nodes and edges are consisted of operations. So it will be natural to begin memory reduction with the operations. To reduce peak memory at our operations, we'll take full forward pass during the search while using partial backward pass for the memory reduction. Take a look at the figure. The red passes only utilize forward passes, which means their intermediate values are not being saved. In contrast, the blue passes will have backward passes, which means their intermediate values are going to be saved. To summarize our method of pass sampling, we sampled operation based on the expectation values of alpha. And that's why we call this expectation-based operation search. Now let's go for the edges. In the same manner with operations, we only utilize partial backward graphs. If you take a look at the figure, you can find blue edges which will save intermediate values, while red edges will not gonna save their intermediate values. Since designated minimum number of edge connection is already fixed, we sampled these edges in pair based on the expectation values of beta. So we call this expectation-based edge pair search. Lastly, we'll work on cells. In scale of cells, we'll only take the backward path for the single cell only, which will reduce even more memory. As we indicated on our figure, The last blue cell of each repetition will have backward graphs, while all the other cells in red will only have forward computational graphs. Basically, we split chain rules to compute them separately for memory reduction, and this is what we proposed as step-by-step backpropagation. Now we are going to check our results from these methodologies. This is our setting for the experiment. As we utilize the few-shot adapted model, we'll use few-shot datasets such as OmniGlout and MiniMishNet with typical few-shot settings. We implemented our solution on Jetson Nano with memory budget near 1 GB. For the server, we used the RTX 3090. Their floating point operation abilities differ in 67 times. Let's take a look into our result table. X here means that we met out of memory issue on target device, therefore we could not check the computation time. As you can see, we reduced our required memory 5 GB to 0.25 GB, almost 20 times smaller. Still, we got comparable performance over various settings at par of 98%. Before we go for our next experiment, do you still remember this picture? If so, it is a expectation-based search. If you are following well, you know we did not update our model at once. However, did it undermine our performance significantly? Let's find out. To briefly give you information, the alphabet Q here means the number of operations we updated at single step. To compare the peak memory first, we can confirm that peak memory significantly differs with the number of operations we sampled. However, if you see the accuracy in this case, you can see that number of operations are not always proportional to the performance. This result indicates that partial updates does not significantly affect our results, showing the feasibility of our approach. Finally, we can go for our conclusion. Thanks for following well. We suggested the utilization of on-device NAS in this paper. We believe on-device NAS will be the adequate NAS for serverless isolated system because it will obviously have more flexibility than training fixed model. As a bright anticipation of our future, we can achieve the scheme of deploy and forget with this kind of on-device NAS, which is the dream of all embedded AI researchers. On-NAS is our answer for this on-device NAS, leaving plenty of possibilities for future works. With three methodologies we proposed, twofold meta-learning, expectation-based search, and step-by-step backpropagation, we achieved 20 times less peak memory and 4 times less storage space. We enabled the first standalone on-device NAS with these three proposals, and we hope this work will bring more progressive on-device NAS works in the future. Thank you for listening, and please feel free to ask questions through email or you can leave comments. Thanks for coming by and see you at the next publication. Thank you.